In this video, we're going to go over the major mechanisms and reactions that you need to know in Unit 5 of Organic Chemistry. At times, you may want to pause the video because I may go faster than you're able to write and try to keep this page organized. This is kind of what I consider our cheat sheet for the Unit 5 test. So the first reaction that we covered was called the SN2 reaction. And with an SN2 reaction, I would like you to know the mechanism. And I'll give you an example. Suppose we had something like this. We know that in organic chemistry, our organic compounds are the compounds that we care about. And so any reagents that we may use to undergo a transformation with organic chemistry, those will be written above the yields arrow. So let's just use sodium hydroxide. And with SN2 reactions, it occurs in one step, and our nucleophile oxygen will come in and replace our bromine. And as a result, it has to attack our electrophile carbon from the opposite side. And so this is known as an inversion of stereochemistry. And so we get just one product. We get our alcohol group as a dash. As a result, we also get sodium bromide, which is what we call a byproduct. Additionally, it's good to note that with SN2 reactions, these only occur with primary and secondary carbons. And for them to occur with secondary carbons, you may want to make a note. So we have a secondary carbon here. The nucleophile needs to be a charged nucleophile. Okay. Now, with SN2, there's also SN1 reactions. And with SN1 reactions, I'm going to have you know the mechanism. And so as an example, say we had this. And with an SN1 mechanism, typically you're going to have a or not charged nucleophile, which is just a weaker nucleophile. And if you may remember, the first group or the first step in SN1 reaction is that the leaving group leaves. With SN1 reactions, rearrangement or shifts, and when I say shifts in this video, I mean your hydride shifts or your methyl shifts are possible. Additionally, like I said, is typically you're used to seeing a neutral nucleophile. And so what we'll get is we'll get a hydride shift here. And then our ammonia, nitrogen nucleophile can attack. When it attacks, it will bring with it anything that it is bonded to. So that nitrogen is bonded to 3 other H's. That gives nitrogen a positive formal charge. We know with other mechanisms, as is the case with this one, our reagent, which is what we put above the arrow, is going to be in excess. And so another one of these reagents can come in and deprotonate that nitrogen. Because we went flat at one point, that means whenever the nucleophile attacks, it can attack from either side. And so what we'll end up with is maybe a wedge methyl and a dash NH2 plus the enantiomer. And so what I'm going to add is we get stereoisomers which is typically your plus enantiomers or possibly sometimes plus diastereomers. After SN1 reactions, we moved on to elimination reactions. And specifically, we did E2 elimination reactions. And like before, like most of these, I'm going to have you know the mechanism. In E2 reactions, they form double bonds. And specifically, they're favored at high temperatures, and we attack the beta hydrogens. So here's an example. Let's say we have bromine, and then we have a wedge there, and I just put sodium hydride. Hydrogen can actually have a negative charge if it's placed next to an alkali metal like sodium. So, and then you might also see that we're at high temperatures. We have 2 beta hydrogens right here. Here's one that is able to react via E2, and then here's another. And on the test, I'll probably ask you to draw all the products, but specifically draw the mechanism for the major product. And so if you remember with elimination reactions and stability of double bonds, the more substituted a double bond, meaning maybe something like tetra-substituted, tri-substituted is going to be more stable than something that's only like mono or di-substituted. And so this hydrogen that is anti-periplanar, meaning it has opposite stereochemistry of the leaving group, is going to be attacked. The electrons are going to fold back and create a double bond, and then our leaving group leaves. This all happens in one step that has 3 arrows. So we get one product that looks like this. I'm going to draw it, but then erase it just for simplicity. If you care to know what the arrows look like for the other beta hydrogen, they look like this. And what that would do is give us our other product, which looks something like this. And this first one is what we would call tri-substituted. And then our other one is called mono-substituted. And this is going to be major. This is going to be minor. But I'm going to add for elimination, what if instead of sodium hydride, we had a big bulky base like potassium tert butoxide? Then what happens is because it's so large, it struggles to get into those small spaces where the more substituted alkenes are going to be. And so basically what I would remember is that major and minor are flipped. Okay, so those are substitution and elimination reactions. Now we're going to get on to many, and emphasis on the word many. There's a lot of them here. Addition reactions. The ones at the beginning, I'm going to have you know the mechanism because I think the mechanism makes sense for our level of organic chemistry, but you don't have to know the mechanisms of literally all of them here, but the ones at the beginning, we will. So the first one is Markovnikov addition of HX, and if you remember, X means halogen. I'm going to have you know the mechanism. So here's an example. First step is our nucleophile, the double bond, is going to attack the hydrogen, which is delta positive in this HBr bond. we're going to place that hydrogen on the least substituted carbon because that will place a positive on their more substituted carbon, and we know that carbocations are more stable when they're placed on more substituted carbons. Additionally, now that we have a carbocation, this molecule has gone flat at that carbon. And so our nucleophile bromine is now able to attack. And because it attacks a flat molecule, we're going to get we'll get maybe a wedge ethyl and a dash bromine, plus it's an enantiomer. Additionally, what I want you to add here is, in addition to knowing the mechanism, we're going to get a racemic mixture. And with the racemic mixture, that means you're going to get an initial product, and then usually it's an enantiomer, but sometimes it'll be its diastereomer, and we'll see that here later. What is not so wonderful about Markovnikov addition of HBr is that methyl shifts and hydride shifts are possible. And we call this anti-addition, which means that bromine was added, and let's call it a dash, but the hydrogen that was added over here is technically the opposite stereochemistry, and that's what anti-addition means. In addition to Markovnikov addition of HX, we also have anti-Markovnikov addition of HX. And we can have a similar molecule to our previous one. And how you know that something's anti-Markovnikov usually is you will see peroxides, which would be two oxygens bonded right next to each other as your solvent. And we get our first reaction that I want you to know how to predict the products, but you do not need to memorize the mechanism. Additionally, we're going to have anti-addition. We're going to produce a racemic mixture. Because this is anti-Markovnikov addition of HX, we should look at our double bond. And we should say this right carbon is less substituted than the left one. And so what that means is that we will add our bromine to the least substituted. Because it's anti-addition, which means the hydrogen that is added should be opposite the stereochemistry of the bromine, which makes this ethyl group a wedge. And then because it's a racemic mixture, we will get the enantiomer. Okay, our next one, I will have you know the mechanism for. This one is called acid catalyzed hydration of water. And for this one, we are going to paste, know the mechanism, and let's say we have something like this. Additionally, H2SO4 dissolved in water is what we might see. And whenever you see that, what you'll do is you'll just simply cross it out and replace it with H3O+. We're going to let my pencil charge up here. We're doing this in one take, so if it takes even a couple minutes, that's fine. You may just have to fast forward on YouTube till you see me writing again. Okay, so H3O plus looks like this. And with this mechanism, you're going to produce a racemic mixture, which means it's got to go flat at some point. And unfortunately, methyl shifts and hydride shifts, which hydride shifts are always favored if possible, can occur here. So our first step is our nucleophile attacks a hydrogen on hydronium. We are going to place that hydrogen at the least substituted carbon, which would be right here, although I'm not going to show that. And then we'll put a positive carbocation at the most substituted. That positive charge, we're going to address it and see left and right if we can make it more stable. That hydrogen can move via hydride shift. And the benefit there is that now we have a tertiary carbocation, and not that it's a benefit, but because it's positively charged, it is flat. Our nucleophile oxygen and water will attack and bring with it anything that it is bonded to. So it's bonded to two other H's, but it carries a positive charge, so water is our solvent. We'll have excess water around to deprotonate. We'll remove a hydrogen, and the electrons in that in that single bond will go back onto oxygen, and we will make our products. And I just picked a wedge alcohol and then a dashed ethyl, and then plus the enantiomers here. Okay, now we're going to do some reactions that you don't need to know the mechanism for. And our next one is going to be called oxymercuration demercuration. Okay, what you need to memorize is more or less the products that they form, and if you see these reagents that you're able to predict the products. So our first one is oxymercuration. Demercuration. And this one is a two-step reaction. In the first step, we'll have mercury acetate dissolved in water. And our second one is that we're going to have sodium borohydride. And for this one, I don't need you to know the mechanism. And it is going to be Markovnikov addition of an alcohol group. What is a benefit of this is that there is no rearrangement possible. So there's no possibility for shifts like the one before, which is very nice. That way, that's one less thing you have to think about. You do produce a racemic mixture. And then our last bullet point is that this is technically anti-addition. So our products are going to be a double bond turning into an alcohol group, specifically the alcohol group being added at the most substituted, so that'd be left carbon. And then we'll get its enantiomer. Technically, although you don't have to show it because this isn't a chiral carbon, with it being anti-addition, the hydrogen that was added is opposite in stereochemistry. We're going to have the same exact reaction, except everything's going to feel a little bit flipped. So let me just copy and paste this. I don't need the name. So copy. Our next one is going to be hydroboration oxidation. And I don't care on the test if you know the names of all of these. I just care that if you see the reagents, you are able to predict the products and complete the mechanism if I've asked you to. So hydroboration oxidation is pretty much the opposite of the one we just did, oxymercuration, demercuration. So there is no need to know the mechanism, except instead of Markovnikov addition of an alcohol group, you might be able to predict, we're going to call this anti-Markovnikov. It does have no shifts. It does produce a racemic mixture, except instead of anti-addition, it's going to be syn addition. Okay, so this one also occurs in 2 steps. We have BH3 dissolved in THF. And then, unsurprisingly, which is common for anti-Markovnikov addition, we have hydrogen peroxide and sodium hydroxide. And if I follow just the steps, it says that we produce an alcohol group at the least substituted. And it's an enantiomer. We don't have any chiral carbons here, but let's imagine an example where we did have chiral carbons. Okay, so no rearrangements possible. So I look to the left and I look to the right. The right carbon is less substituted, so I'll put my alcohol group there. And technically, the hydrogen that is added needs to be the same stereochemistry since it's syn addition, which makes that original methyl group have to be a dash, and I can say plus E. Okay, our next one is catalytic hydrogenation. This one, no need to know the mechanism. Just gonna copy these over. This one, you don't need to worry about anti-Markovnikov because this one adds hydrogen at both carbons. So this is going to add H2 across a double bond. You don't need to worry about any shifts. It's going to be a racemic mixture, and you are going to get syn addition. So hydrogen alone by itself does not have large enough of an electron cloud to make it polarizable. And so we need a catalyst to make this happen. Oftentimes you'll see like a transition metal like palladium. You may even see it say high pressure. And all we're going to get is hydrogen. Oops, almost made it an alcohol. Hydrogen and hydrogen added across a double bond. Because it's syn addition, they have to be the same stereochemistry, which means that this methyl group, kind of like before, is going to need to be the opposite stereochemistry, and then plus the enantiomer. Okay, got just a few more, promise. We got halogenation. And with halogenation, we're going to take something like, let's say this, and react it with some kind of halogen, not fluorine. Fluorine technically doesn't work here, but let's say Br2. Could also be Cl2, I2, something of that sort. And I want you to know the mechanism. And we're going to get a racemic mixture. Benefit of this is there's no rearrangement possible. And it's going to be anti-addition. So our nucleophile double bond attacks one of the bromines. Even though bromine's nonpolar, Bromine has such a large polarizable electron cloud that at times one of the bromines could be delta positive for just a fraction of a second. And we're going to put one of the bromines that was attacked on the bottom carbon in the double bond, least substituted. That way our positive charge is on the most substituted. Even though bromine technically forms a partial bond there, we don't need to stress over it. Instead, just think of the other bromine as coming in and attacking this. This molecule does go flat. And so when it attacks, it can attack from either side. And we're going to get Br, and then methyl. Let's focus on stereochemistry. These bromines need to be opposite stereochemistry, okay? That is what anti-addition means. So one of our products might be wedge bromine. The other is going to be dash bromine, which means that this methyl has to be a dash since you can't have two dashes on one carbon. But the methyl over to the left that we started with was never touched. Therefore, it needs to stay a wedge at all times. And so this would be a case where plus E would be incorrect. And rather, what you might do is keep that wedge methyl the same, switch your bromines and that other methyl. And this would be called plus D because it's a diastereomer, because not all of the stereochemistry has changed. Let us do the same exact reaction, and I'm going to have you know we want halogenation, except this time, instead of bromine, let's make it, oh, I don't know, something like this. I do want you to know the mechanism, halogenation with water. Then I'll do halogenation with an alcohol. And let's make it iodine. Oops. And then let's dissolve the iodine in water. So our first step is the nucleophile double bond attacks one of the iodines with great polarizable electron cloud. Just like before, we're going to put the positive charge on the most substituted and iodine on the least substituted. There is no rearrangement possible, so we don't need to worry about that. And we've talked in class that oxygen is a better nucleophile than any kind of halogen. So oxygen will come in and attack that double bond. As stated earlier, oxygen will bring with it anything that it is bonded to. So in this instance, it's going to bring a whole water molecule. And additionally, water will come in and deprotonate. So what we'll end up with is, oops, just erased, methyl, alcohol, iodine, and then we've just got to follow what we know since some things went flat. Is that with stereochemistry, we're going to get something where the alcohol and the iodine have to be opposite stereochemistry. That's what anti-addition means. Leaving this methyl to be this. And because there's no stereochemistry on any other part of the molecule, I can, in fact, say plus E here. Now, I'm going to do the same exact reaction. Almost literally the same, except I'll change just a couple things. What if we had halogenation with an alcohol? And I'll be simple and I'll just have like ethanol, which is a very common alcohol. And just for some differentiation, I'll make this chlorine. So our first step is we're going to put our positive charge at the most substituted carbon, where chlorine is added at the least substituted here. And then oxygen, which is still a nucleophile, whether it's in water or in an alcohol, is going to attack and bring with it everything that it's bonded to. So that's an H and an ethyl group. Oxygen is not going to stay positively charged, so the solvent, which is ethanol here, will come back in, deprotonate. And like before, this actually forms an ether. Okay, since oxygen only brought it with one hydrogen, and that hydrogen was deprotonated in the last step. Additionally, we have anti-addition, so call that chlorine a wedge, which makes this oxygen a dash, which makes the other methyl a wedge, and then you can say plus enantiomer. Okay, we've got two more. These are the ones that we did at the start of class on Monday. This one is ozonolysis. What this does is it oxidizes your double bond. So I'm going to say split your double bond. And specifically oxidize the carbons. And you're going to form, as a result of the oxidation, a ketone and or an aldehyde. So let's see how this works. I don't need you to know the mechanism. Okay, so I have three examples here just to show you kind of how this works. Our first one looks like this, and we have two steps. Our first one is to have ozone, which is actually a gas, and then what I call, oops, not B, but DMS, dimethyl sulfide, which is CH3, 2S. You don't need to know the mechanism. So what I like to do is slice this in half, and I want you to redraw it, except with the double bonds. I want you to kind of split the double bond and make it something like this, wherever the double bond was, understanding that this is where it was sliced. So what these two products look like then, and actually I'm on iPad, so I can actually easily kind of separate them, would be two separate products. These are both aldehydes. So that is example number one of how to do ozonolysis. So you get an aldehyde, which is common. Okay, let's do another one. On this next one, I have something very similar, but it is a little bit different. Again, our step one is ozone, and our step two is dimethyl sulfide. We will split the double bond, and I'm going to redraw it. This just makes it easier. Where the double bond was is where I put my two oxygens kind of in the middle where it splits. Then I can put them. Actually, this carbon is bonded to two other carbons, so when that happens, we call that a ketone, and we get another ketone. And then our third example, a little bit tricky, is going to be a ring structure. So imagine if you open up a ring or split a ring, because it's connected at two spots, you'll still only have one molecule at the end. It'll just not be cyclic anymore. So what I'm going to do is I'm going to split it here, and I'm going to redraw it. And now, what I like to do is I like to count my carbons because I want to unwind this kind of wannabe ring. It's not truly a ring. So I got 6 carbons. So I'm going to translate that. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. On carbon number 1, there's just a double bond. And then if you wanted to draw the hydrogen, you could. I won't. On carbon number 2, there is a propyl, 1, 2, 3. Carbon number 3, there's a methyl. On carbon number 4, there's nothing besides 2 hydrogens. On carbon number 5, there's just a methyl. Then on carbon number 6, there's just a double bonded O. And so there's what the product would actually look like. Okay, so this is a cyclic ozonolysis. When you go ahead and do, I think it's skill set 12, ozonolysis might be the toughest one sometimes to predict the products. And then our last family of reactions, still alkenes, but is going to be glycols. Glycols is just another fancy name for diols, meaning that they're going to add 2 alcohol groups or 2 OH groups across a double bond. And because each carbon is getting an alcohol group, you don't need to worry about Markovnikov versus anti-Markovnikov addition. Because each carbon is getting their alcohol group, there's not one that gets one where another one doesn't. So we have our syn glycols. That is going to be osmium tetraoxide dissolved in water. And so this is going to be a racemic mixture. And like I said earlier, it is syn addition, meaning that the alcohols need to be same stereochemistry. So I draw everything with no double bonds. I usually start with wedges. There's one, there's another, that makes it a diol. Then I can say plus an enantiomer. And then our very, very last one is going to be anti-addition. And so what I'm going to do is I'm going to copy this. Oops. And some things are going to change. We're going to get new reactants. We're going to get rid of syn addition, and we're going to change it to anti. And the easiest way I know to do this is to take a baking soda solution, so NaHCO3, and then an acidic solution that has excess H3O+, and all that that's going to do is make it anti-addition. So one of the alcohols needs to be dashed, and then you still get a racemic mixture, and you still get an enantiomer. And that's it.